Hi, my name is Neha Radhakrishna and this is my presentation of my term project, that is implementation of NEOS 2 softcore processor. These are the things that I'll be covering during the presentation. The first one is, what is a softcore processor? A softcore processor is an intellectual property and it can be implemented using logic primitives of FPGA, and this is basically a microprocessor that can be implemented using logic synthesis. Why exactly do we use softcore processor? One, because it is very easily configurable. Because of this configurability, it can the technology doesn't become obsolete. That is, you can keep updating the technology, and also you have a lot of time to market the product and thus increase the gains or profits of the product. And also it can be easily integrated onto the FPGA fabric. NEOS 2 is one such softcore processor, and it is the most widely used processor in the FPGA industry. And the four main reasons is that NEOS 2 softcore processor is highly flexible, it has high performance, and it has low cost and long life cycle. So next we'll see the architecture of NEOS 2 processor. It is a 32-bit processor which follows Harvard architecture. It has 32 general purpose registers and 6 control registers. Arithmetic and logic operations are performed using these 32-bit 32 general purpose registers. So when it comes to addressing these operands, the following modes are used. That is immediate mode, that is an offset is present in the opcode itself. Register mode, where registers are used. Displacement mode is a combination of immediate mode and register mode. And register indirect mode is the effective address is obtained by adding the displacement and the contents of the register. And absolute mode is also a type of an immediate mode, addressing mode. Instruction types, the instructions can be of register type, or register immediate type, or a jump instruction. And the instructions are classified into arithmetic, logical, jump, load, store, and shift instructions. Arithmetic instructions, as the name suggests, is used to do arithmetic operations. Logical instructions are used to perform logical operations. Jump is basically conditional statements. Load and store, whenever you need to load data onto the memory or store data into the memory, you use load instructions. And shift, if in case you need to shift the number of bits, we make use of shift instructions. So basically there are three types of instruction formats in NEOS 2. First one is the I type or the immediate type. So as we can see, the 5-bit the opcode is made up of the last 6 bits, and the first 5-bit fields are A and B registers, and they are used to specify the general purpose registers. Apart from that, there is a 16-bit immediate field which provides immediate data, and this can be sign extended up to 32 bits. Next is the R type. Again, the first 5 bits are used to indicate the opcode, and the MSBs, that is MSBs are used to indicate general purpose registers. An 11-bit field OpX is used to extend the opcode. J-type is used for jump instructions. A 26-bit field immediate 26 contains unsigned immediate value, and this is used only for call instructions. This is the architecture, that is and it consists of instruction memory, registers, sign extensions, muxes, arithmetic logic unit, and data memory. So the architecture can be classified divided into 5 pipeline stages. The first stage is a fetch unit. In the fetch unit, the instruction is fetched and also the program counter is implemented. In the decode unit, the instruction is decoded and then it is it is pushed on to the registers, and also if there is a sign if any sign extension is needed, that is done in decode unit. In the execution unit, the instruction that is decoded is executed and sent on to the arithmetic logic unit. Next is the memory unit. That is, if the data has to be stored into the memory or written into the memory, it is done in the memory unit. If there is any instruction that needs to be fed back to the fetch unit, it is done in the write back mode. Now, I have considered two programs, that is dot product benchmark program and factorial program. This is a dot product benchmark program. Here, two vectors are taken and then a multiplication is done, and these are the set of instructions and the type of instructions that I've taken, and the final result is as shown in this waveform. The total answer would be 580, the dot product, the product of the dot product multiplication. The design, how I've designed is, there are 5 different files, that is fetch, decode, execute, memory, and write back. All of these files are written in Verilog. During fetch, the instructions are fetched from text file, and during decode, the decoded instructions are written onto the register file, and during the instruction stage, the data is stored in the data memory text, and all of this is included in the main module, that is neos2.v. And to verify my program, I've created a test bench and run the tests, and that's exactly how I got the waveforms as shown here. Next is data forwarding. So data forwarding is a way to make sure that the data is being processed at the right time. Next is the factorial benchmark program, and here the factorial of 5 is calculated, and the type of instructions is as shown here, and the answer is as shown in the waveform. So since it's factorial of 5, we have the 120 is the answer, which is shown here, and this is incrementing and decrementing of the stack here. And as a conclusion of this as a conclusion, what I learned from this is that I got a strong fundamentals of MIPS programming and NEOS2 architecture, and also I had hands-on knowledge about MIPS and NEOS2. Thank you.